seminar by Dr. Sayan Damas, that most of you already met at this lab. So, first of all, it's my great pleasure to have Sayan here and, working in Lincoln on the European project, and working with us for some time now. So, Saria, actually, she's from Lebanon. She graduated in mechanical engineering at the University of Notre Dame in Lebanon, 2013. Then she did a master in advanced robotics and Marie Curie University in Paris, in France. And after that, she did a PhD inside in Italy, in Pisa, still in robotics. And that's probably where you learn Italian. Right?
I guess.
Okay. So she did PhD in Pisa, and then she went to join us at that time when I was in Lincoln, to join us in ICAS to work on various robotics projects, starting from 2019, right? And after a couple of years, in 2021, I think started to work on the European project part. And most of the work now that she's going to present today is, I guess, related indeed to that project. So again, great pleasure to have you here, and looking forward to the presentation.
Thanks, Nicola, and thanks for welcoming me between you. It is also my pleasure to be between you. So, in today's talk, I will be mostly talking about my activities during the last 3 years in Lincoln. I am part of the Lincoln Center for Autonomous Systems, which is directed by Professor Mark Hanheide. He is also part of the European project DARCO, where the PI is Nicola Bellotto and Professor Nicola Bellotto and Professor Mark Hanheide, and where we have also a PhD student, Luca Castri. Maybe you met him before, working also on DARCO, and sometimes from time to time there are students, master students doing their projects in it. So to start with, DARCO, the final aim of DARCO is to optimize the operations and logistics domain. By optimizing logistics, the operations and logistics, they want as final aim to embed the robot with capabilities to launch an order in a tray on a conveyor instead of going next to the tray and place the order in the conveyor at a short distance from the conveyor. So this is the final aim. We have multiple international partners on DARCO. Other than Lincoln, there is ETH in Zurich, there is TUM Technical University of Munich in Germany, there is Bosch Research Center in Germany, Orbro University in Sweden, and Pisa University from Italy, and other partners. I will speak about Lincoln activities. From Lincoln side, we are responsible of developing reasoning algorithms of the robot, more specifically reasoning on the interactions that happens in its environment, and also on the cause-effect variables or factors that are contributing to the evolution of the dynamical system in the environment. The reasoning on the interaction and on the cause-effect factors that is happening in the environment help in increasing the safety while the robot, the autonomous robot, is navigating between human operators and logistics. So this is the final aim. And we saw that the first problem that we saw is that although there are good benchmarks that have been developed in order to reason on the interactions between multi-agents or operators in the logistics, and to reason about their motion, there are still some room in order to enhance or to optimize their performance. One of the problems that we saw is in the task of context-aware human motion prediction. The first problem is most of the benchmarks that have been developed in order to reason on the context-aware human motion prediction, they give an equal weightage or an equal importance to every individual that is in the neighborhood of a single agent. And we hypothesize that we don't have equal importance to each single agent that is around us. Maybe one agent that is coming next to me and near to me will affect my future motion more than a person who is further than me. So based on this hypothesis that we want to test, and we want to test that by incorporating unequal weightage of the individual context in the human motion prediction, we are able to get a better accuracy of the predictive model. So in order to do this, so our hypothesis or our approach is to weight unequally the context or the interaction between pair of agents in the scene. And in order to do this, we rely on the qualitative interaction instead of quantitative interaction representation between a couple of agents. And why? Because qualitative interaction, it is an intuitive approach in order to understand the intent communicated between agents through their motion. So it's not verbal intent communication, but it is an intent that is implicit in their motion. Okay, and in order to represent qualitatively the interactions between pair of agents, we rely on a calculus from the literature called qualitative trajectory calculus. This qualitative trajectory calculus represents qualitatively the interaction between a couple of agents by assigning to them the label of, if two agents are going next towards each other, they are going away from each other, one is going to the right, one is going to the left, one is going at a higher speed than the other, or one is going at a larger angle with respect to another. So this is what does it mean, qualitative interaction representation. And in the literature of qualitative trajectory calculus, we can represent the state. We call them states, so they are QTC vectors. You can see them like this vector or this tuple that is here, which is made from 4 symbols, for example. This is called a QTC vector. Those QTC vectors are also a state. It's a qualitative state representing the interaction between a pair of agents. So those QTC states here, they can be represented graphically with this graph, which we don't, of course, we don't see anything from it, but this graph is made from nodes and from edges. In order to simplify what is there here, this is a subgraph out of this one. One node is a QTC vector, and it is connected to all possible future qualitative states given the current state. So given that a pair of agents are in this central state, qualitative state, some future qualitative states are not possible, so the space is limited to those 15 states. So what we did is that we say that we want to represent the likelihood of a future state, qualitative state between a pair of agents given the current state. So this likelihood of transitional likelihood from one state to another state, we want to label it as alpha. So we call it alpha, and this is calculated as 1 over the total number of possible states given the current state between two agents. And this will serve as a label for the interaction between a couple of agents in a neural architectural model. So what we did is that we collect all the possible alpha spanning a 2D space, and we store them in a dictionary. And then the neural network, inside the neural network, which this approach can be applied to any model architecture, but you need to go and change a layer in that model. So it can be applied to any neural model, but you need to change one layer of that model. So it goes, this one layer, it goes to search in a dictionary what is the label alpha corresponding to the spatial interaction between a couple of agents. And how we did this is, suppose we have two agents A and B, there is a spatial interaction between them. Their interaction is represented as an embedding or a dense layer of their relative position. So what we did is that we go to search for the alpha label corresponding to the qualitative interaction, which is QTC that we calculate, and we multiply the embedding of the relative position between a pair of agents with that alpha. So this is what we do on a practical level. So I think I explained a bit, but I need to do this in order to understand for later on. So the QTC is usually on a lower level. The QTC has multiple types. Some of the types are C1 and C2. The difference between them is in the number of symbols. So it is 1 to 4 or 1 to 6. So it encompasses, here there are 4 symbols. So it is QTC C1. But there is other types of QTC like QTC C2 that can have six symbols. And by 6 symbols, there is the velocity and the angle. So you have more, you are enriching the information for the neural network. The first, like I will give an example between those two, blue and yellow agent. There is this triple made from 4 symbols. The first one represents if the first one is going towards or away from each other. The second symbol represents like the yellow is going towards or away from the blue. The third one represents if the yellow is going to the right of the yellow or to the left or in the same direction. And the final one represents the opposite. With QTCC2, you have 2 more, which are angles and velocity. Okay. Yes, and each symbol, Q1 to Q4, can their values span the discrete space U, where the value can be either -0 or plus, but for computational reasons, the minus is, of course, is replaced by -1 or minus whatever it is. Plus is plus 1. So that's it on the lower level. And then, okay. So we tested this approach. I said that this approach can be implemented or integrated in multiple architecture, neural architecture. But we tested on 2 benchmarks from the state of the art for context-aware human motion prediction. The first one is the ASGAN. It is written. Yes, ASGAN is the social generative adversarial network. But this SGAN, it concentrates only on the dynamic context, so there is no, inside this architecture, there is no static context in the environment, trees, something like this. It is one of the best benchmarks for context-aware human motion prediction. There are others also good as this, but it is one of the best performance that it shows in terms of time, complexity, or the inference time, and the accuracy. What this does is, of course, it has a generator and a discriminator. The generator has an encoder that encodes with an LSTM layer each person in the total scene. So the red is one person, the green is another person, so that it predicts the motion of all the people in the scene at the same time here at the end. So you have the encoder that embeds the state of each agent alone. Then all of these goes into a pooling layer, which pools the state of one of each agent given its context. So it is here where the context of each agent needs to go. It outputs 3 concatenated vectors, which I will speak about them, and those enters into a decoder, which decodes the hidden state of each agent, and it generates fake trajectories. Fake trajectories goes into the discriminator, which has an encoder of LSM encoder, and this will discriminate if the trajectory given are real or fake. So this discriminator has 2 losses: a loss for the real trajectories given, so it needs to classify the real trajectories as, or the ground truth as real. And it is given another loss for the fake trajectories generated by the generator, and it needs to classify them as fake. So this loss is a cross-entropy loss function, and the loss of the generator is the root mean square error between the ground truth and the generated trajectories. So our approach is in the pooling, our contribution is in the pooling module, because the pooling module It output, so the middle vector here is the same as the hidden states that are the vector of the hidden state that is embedded. It is this. And then this is concatenated to another vector which takes into consideration the context. So this vector here is the embedding of the context agents, which are the dynamic people around the central agent. So the pooling layer is this one. So what it does is that it calculates the relative position between each couple of the neighbor and the central agent. It embeds them with an MLP, multi-layer perceptron. Then it is here where we add the alpha, the label from the QTC that I spoke about. It goes to multiply the embedding of the relative position here. And then this will be concatenated, it is similar to here. So it is concatenated to the input and then concatenated to another noise vector in order, a Gaussian noise, in order to generate multiple possible fake trajectories. And then because we cannot, we need one representation output from each agent, there is at the end a max pooling that pulls those concatenated vectors into one single representation at the output. The testing was done on open source datasets, which are the benchmark dataset done for the benchmark architecture, used in the benchmark architecture. They are they incorporate a university campus, Zara Street, Hotel Street, and the ETH campus. The perception sensors are, for part of those dataset is a fixed top-down camera, like this one here and this one here. But for other datasets, within those is driven by a mobile stereo ring on a car that is moving in the city. The results, we have two metrics for the results. One of them is the average displacement error on the predicted trajectory. And the second one is the final displacement error, the goal where the person will reach. We have the results over the 5 data sets that I spoke about, and we have the mean over the 5 data sets. We have the baseline, we have the neurosymbolic, we call the neurosymbolic approach for the SGAN, and we have the relative gain of the neurosymbolic relative to the SGAN. So we have a relative gain of the average displacement error with the mean over the 5 data sets. It is 60% over the shorter term and 78% over the longer term. The FDE metric, the final displacement error, has a relative gain of 58 on the short term, 76 on the longer term. And we have the standard deviation for the ADE and for the FDE. With a standard deviation, the mean, the relative gain by applying the NeuroSim approach is 28% and 43%. And for the FDE, it is 33 and 46. We have some qualitative representation of one of the scene where we only concentrated on having 6 individuals, the 6 individuals. We have the ground truth, the baseline SGAN, and the NeuroSim SGAN. If you want to look only on the blue person, maybe I should. It doesn't repeat, but we can see that even for the final displacement, the blue trajectory, the predicted trajectory, is this one is closer to this one than this one. Okay, it's not the only one that can infer the result, but I mean, the results prove that the approach of embedding symbolic knowledge in the neural network is better than the baseline. We have another, we tested on another architecture, a baseline architecture for now generic time series forecasting. It's a generic time series forecasting, and this has integrate a dual attention recurrent neural network. By dual attention, I mean an input attention and a temporal attention mechanism. By input attention, the network gives attention to which agent in the context more than the other. By temporal attention, of course, it gives attention to which time more than the other time. So how we did this architecture is tested on a data set from Stanford University, which is called a Jackrabbit data set. It has like cafe scenarios and it has poster session scenarios on the university campus. And this data set specifically, it is not like the others because it is collected from a robot mobile sensor, the Jackrabbit data set. So there is a robot moving around and collects, it has a LiDAR sensor and a fisheye camera sensor. Because the scene cannot can grow exponentially with the number of people that enter and goes, and the neural networks needs to have a fixed size of input. To deal with this variable size of input to the network, we did a clustering technique. So we generate clusters around each agent with a specific radius in order to limit the number of agents that can affect the motion of the central agent. And of course, here the question is, what is the radius that you used? And for this, we relied on the literature of the proxemics, which deals with it's a study on the distance at which people will interact together. And the radius can range from 1.2 meters for the social interaction to 3.7 meters if I remember well. So this is the radius. We have all the agent observed time series of the agents input to the network, and the output is the predicted trajectory of the central one. The input attention has an input attention layer, which is a dense layer. It gets into a softmax, and then LSTM encoder. Then in the temporal attention, we have a temporal attention, softmax, and then LSTM decoder, and then we have the LSTM decoder is predicted, it has cells over future prediction time. The input that we did is on the output of the input attention. It is like let's say it is similar to the embedding that you saw before of the position of each person. Of the time series motion of each person. And then this gets multiplied in a CMD, which is alpha CMD that you saw. It gets multiplied with the alpha CMD that is queried from a dictionary based on the qualitative interaction calculation. The results for this is, okay, the dataset I spoke about it is the Jackrabbit. And the results are this based on the matrix of the root mean square error and the mean absolute error of the ground truth predicted ground truth trajectory, future trajectory, and the predicted trajectory in the future. We saw that there is a relative gain of 22% on the shorter term, which is 3.8 seconds of the root mean square, and there is a small degrading in the performance of 4% of our approach for the root mean square error, and the mean absolute error is a degrading a small degrade of 3% on the smaller time horizon, and on the longer horizon it is 21%. So the overall gain of our approach is bigger, even though there is here a small degrade which can be tested in the future with the because the root mean square error infers how much outlier you have, and this is on the 4.87, which is the longer term. So it can be tested for a better performance by studying the effect of the radius of the cluster on the performance of the network. It is a hypothesis to be tested. Okay, now after the symbolic knowledge embedding, we wanted to test if we embed a causal information about the variables that are helping in evolving the dynamical system of the environment. So if we add now a causal knowledge about the environment instead of symbolic knowledge, whether the performance will be better, equal, or worse. So this is a work led by the Luca Castri, if you met him before, and he works on the causal discovery in the environment. So what is the causal structure of the environment? So what are the cause variables that are what are the variables that are causing other variables, and what are the variables that mostly represent the dynamical evolution of the environment of the robot. So just a brief 2 words about this. What Luca did is that for time series data, there are causal discovery algorithms like PCMCI and PCMCI plus. It is specifically for time series data. This can be, by causal discovery, you can represent it graphically with like this one. It's a directed acyclic graph. And it can be represented with a structural, it's an algebraic equation, so a structural causal model like this one, where there are the effect variables and the causal variables as the parents of the other variable, and some noise factor. And then there is a test which is called a mutual conditional independence test, which tests the independence between two variables given their parents, and this will tell if there is a link between them or not and how the link is directed. So this is briefly, but what Luca did is that he PCMCI and PCMCI plus takes time usually in order to generate this causal graph. And for robotics application, you don't have a lot of time for real-time operation. That's why we tried to enhance the time of the computational time to generate this DAG by incorporating by adding a transfer entropy based filter before giving the variables to the PCMCI. So usually you give all the possible variables that represent your environment to the PCMCI. Let's say all of these variables, like the distance between agent A and the goal, the angle between the orientation angle between the agent A and the goal, let's say the shelf, and the velocity, the absolute velocity of the agent A. Let's say those are the main variables that cause the evolution of the system, but there are other variables that don't cause the evolution of the system. Let's say those ones. So if you apply a transfer entropy filter at the beginning, this one finds the variables that are correlated together, but not the causation field variable. And it helps into filtering out what are the variables that are necessary for the PCMCI. Given this, then you get to the PCMCI, it generates you the DAG, this DAG, and it will be a more accurate DAG in terms of the links will be more accurate links, so it's not a spurious links between them, and the computation time is faster. Okay, this is what Luca generated here, which has less links, which are the true links that should be generated, and in less computation time. I skipped to this because I spoke a bit about the causality because given what I spoke about before, and given that there is, for each link here, there is a causal weight. It's not equal to causal weight, it's causal effect of one variable on another variable, and let's say this causal effect is denoted by alpha again, but it's another alpha now, it's alpha causation. Then if you remember, when we embedded here, there is concatenation of vectors in the SGAN. So if one of the vectors is the embedding of the motion of each single person, then it's concatenated with the alpha from the symbolic alpha, so the TTC alpha, which multiplies the embedding of the relative position between agents. So all of this is from before. And then what we tried to do is we added a third vector concatenated to this from the causation now. So there is an embedding of the variables, which are the variables that are causing the motion of a single person. What is causing the motion of a single person? Like its velocity, it can affect the motion of a single person, the distance to the nearest neighbor, and the relative angle between the central agent, and the nearest neighbor. Let's say that those variables are affecting the motion of a single agent, then they got embedded, then we get the alpha causation from the causal graph that we saw before. And then we test the concatenation of this with all of this, and then max tuning at the end. But what we get is, we get that, so this was the baseline, this is the baseline, and QTC embedding that I spoke about before, and it was better than the baseline. But with causation only, we get a performance a bit similar to the QTC performance. So it is good, but it didn't beat like the QTC. There is still no study that needs to be ongoing study in order to see where the causation can, or maybe if we embed the causation in a different manner than what we did, then maybe we can get something better with the causation than the QTC. For example, I tested also with not observing, so the QTC and the causation, not embedding all the observed time series, but only the last observed time. And I got also a good performance with this one. But here the point is, I need to see the inference time of this with one observed time, embedding only one observed time compared to all of the others. So maybe here, if we embed other metrics like the inference time, maybe we can get an advantage of incorporating also the causation in addition to the QTC. Okay, I'm a bit in short. I will try to accelerate this. The other problem that we worked on is, instead of predicting the motion, how about predicting interactions? By predicting interactions, it's a bit different than predicting motions, because predicting interactions, the robot can infer on the intent communicated, as I said before, the intent communicated by the motion of people, which is implicit in the motion, in their motion. So with the prediction of a motion of a single person motion, you cannot predict the intent communicated. But with a prediction of interaction, you can predict an intent. So for this, what we did is we compared. Okay, I'll be faster. We compared the three. We did a benchmark. So a benchmark of the same architecture of the neural network, but with different variants of it. The first benchmark, it's the dual. We tested this on the dual attention neural network that we saw before, which has input attention, temporal attention. So the first version of that benchmark is we input indexed QTC tuples that we saw before, indexed because the QTC are categorical data. So we need to get an index for each tuple. So we input the observed time series of QTC, but in terms of their indexes, instead of, because we cannot give a tuple. So we input QTC series of the all agents in the cluster, and then we output directly the predicted QTC. And this was QTC C1, which has 4 symbols. For the second variant of the benchmark is the same as the first, but QTC C2, which has 6 symbols, so more information. And the third one is, instead of inputting QTC, we tested, okay, let's input the normal motion, the time series motion. We don't input interaction, we input motion. And we predict motion, we predict time series of row coordinates as the normal architectures. And after this, we post-process the predicted motion with a predicted interaction. So it will be a post-processing. So the comparison of this, okay, I said it will be qualitative because I am using QTC because inputted for intent communication. I stick to this, and it is tested on the same dual stage attention neural network that we saw before. However, it's not I predict now only the single agent, because I want to predict interactions. So I want not only one agent as the output, I want the interaction. So it's the same dimensionality of the input, not like the other one. it is the same dimensionality of the input, it is the same for the output, because I want to predict pairwise interaction between couples of agents. Okay, and we tested on the Jackrabbit dataset for two scenes. One is the cafe scene, and the other one is a poster session. I skip. For the results, is the metric is the distance between two QTCs. What does it mean? It is the QTC that is the ground truth QTC of the prediction QTC, and the other one is the predicted QTC, which means the predicted qualitative interaction. We have this distance as metric. For the cafe scenario, we saw that the architecture where you input time series data and you predict time series data and then you post-process them with 4 symbols shows better mean and standard deviation for the radius one, which is 1.2 meters, so the shorter distance. And also for the radius 2, which is the larger distance, which is 3.7 meters. This is on shorter time horizon prediction. The other blue is on the longer time series prediction, where we saw that the time series input is better than the other one, but with more information. So 6 symbols of the QTC gives better performance on the shorter radius, and with 4 QTC only symbols, it is better on the larger radius. Okay, then the poster session, we have also better performance also on the poster session with the time series input of 4 QTC. So this one, the third row from here and the third row from here, shorter time horizon, longer time horizon. And then we did for the PS1, it means the transfer learning. Here there is no training. We did the transfer learning from the poster session 2 to poster session 1, which are different but similar domains. And we got on the 100% dataset of the poster session 1, we get also the best performance is for time series framework with 4 QTC, and the performance didn't degrade with respect to poster session 2. Another problem that I am currently working on, which is a work in progress. So there is a bit of preliminary results here, but they are not final results that yet. So we are working on the reasoning on the risk level in the scene. Given the operators have some activities in logistics, some of the activities are risky on the, let's say, on the health or ergonomics of the operator. Other activities are non-risky. Some of the risky activities, for example, is loading, unloading of boxes. Other activities that are non-risky, like conversational group, speaking, desk level activities, throwing something like this. We leveraged on the health and safety risk assessment documents in order to label the scene if it is risky or not. There are multiple factors that should be taken into account for labeling this. One of them is what is the load that the operator is carrying, what is the frequency of the operation, during which how much time the operation is taking place, and the environment conditions like lighting, the surface, if it is slippery or non-slippery. Okay. Those are the factors in order to label the scene if it is risky or not. What we are doing is we are benchmarking two approaches: a causal graph attention approach with a non-graph approach. For the non-graph based approach, we are relying on the one of the latest state-of-the-art in classification of the scenes, which is a vision transform. So this is a vision transformer from the state-of-the-art, but it has a causal explanation of the prediction. It has causal explanation because it shows you at the end. Okay, I will not now go into the details of this, but I can do later. It outputs a saliency map, which shows you the effect, the contribution, the causal impact score of each pixel on the prediction class of the network. Like for example here, if it is it's one kind of fish, but okay, the saliency value is the highest for those pixels that are here, and this this saliency value of the red one here is given through a calculation of a causal impact score. It's called causal impact score, driven by the calculation of the effect of each pixel on the prediction output of the network, which is taken from the masks that are agglomerated from the feature maps of the transformer encoder. So you take the last feature maps of the transformer encoder, they cluster them in order to reduce the redundancy in the depth level. They normalize them, they upsample them. Then there is a bit of debiasing and calculation of the effect of each pixel in the output. Okay. Something preliminary, not yet to expand on it. For this, we have collected a custom data set for activities that are similar to the activities done in logistics. And we collected this data set in the laboratory in Lincoln, where we have some activities of loading, unloading, and some other activities of desk activities, as I mentioned to you earlier. And we did this, we labeled each image based on the risk assessment that I spoke about. We didn't do anything yet here as a contribution, but we did the training and testing on the custom data set. What I want to show is that here, which is the predicted, there is a risk, 1 is risk, 0 is non-risk. Here, for example, the user is loading, unloading a box. It is true there is a lot of red sparsity of the red here, but there is more red on the posture of the person, which is around the load. Here there is the person putting a load on the shelf. There is a big red region on the boxes and the shelf and on the poster, but there is also on the desk. It should not be there. So we are still working on this, but I am shifting from the vision transformer to the video vision transformer, because with the video vision transformer you have the frames, and we want the frames to incorporate the frequency of the operations of operators. With the images we cannot do this. We don't want to show the best performance with the causal explainable video vision transformer, but we want to benchmark to this. What we want to benchmark to this is the classification of the graph. So we want to run a graph attention network. You can find the graph attention network from the state of the art, but our contribution to this is the if you know that this is also this from the state of the art. If you have the node is the object detected from the scene, let's say the object is the joint of the user that are embedded in those nodes, and then the link between the nodes is the attention between a joint and the object. Let's say I embed here the box, and I embed here the wrist time series. Then the attention between them is usually in the graph attention network learned from the network, right? So what we want here is to give this weight as a causal weight from the causal discovery that we saw before, and test the performance of the classification of the graph based on this new architecture. Where we are at this point, because we are running the two approaches in parallel, or we are working on the two approaches in parallel. So at which stage we are here? We are at the level of dataset. It was already annotated. We run the open pose for the pose estimation of the user in order to extract the time series of the joints that we want to embed in the nodes of the graph attention network. And we run a detector, which is the YOLO detector version 4, on some classes that are specific for logistics, like boxes, door, yeah, person, tool drawer, plastic bags, and something like this. So this is our stage in this. I will skip. I still have only two slides, and I'm done. Okay. Okay. Um, okay. So what I am trying to do here in the 2 weeks is I am I am sponsored from the Alan Turing Institute in UK in order to have an exchange between UK and Italy, and I think it has the opposite way also from Italy to UK. And so the topic that I need to work here on is on trustworthy AI. And the proposition is to extend the explainable risk, scene risk classification. Let's say it is explainable because there is the causality embedded there, and the causality is already explainable, implicitly explainable, because if you draw the causal graph, you can explain that one variable is affecting another variable. Or let's say the explainability with the vision and video transformer that we saw before. So if I am at this stage, the extension of this word can be on the robot has classified the scene as it is risky or not. But then what he needs to do, he needs to ask if it is risky, then he needs to approach the operator and ask, do you want to help and what do you want to help in? So it's let's say a verbal interaction. And in order to make it trustworthy, we are trying to, there is no more trustworthy than including the human user in the field. And it is not final, but the proposition is to ask more questions the user what he needs help in, and ask about the, let's say, the robot approaches the user and says, do you want to help? And then the robot will say, the user will say yes. And then the robot will say, what do you want to help in? And the user will say, I want to pick the box from the shelf that is at the right, for example. By speaking about trustworthy, I think we can do, the robot can ask more questions to the user in order to get more semantics of the object that is in the shelf, because in order to not each time going to pick a box and then the robot may pick the wrong box, not what the user wants. So you may find, for example, two bottles, let's say, of water that are both of them green. One is lighter green and one is darker green. But usually the person, if you ask a person, what do you want? And then he said, I want the green bottle from there. The person will not say usually, I want the lighter green or darker green. And the person doesn't know which, if the environment has changed during time. So if there are more objects that are similar to what he wants there in the place where he wants to ask for. So it's a current word which is not, during those 2 weeks it was developed, it is not something that final, let's say. But the state of the art states that for an AI decision to be trustworthy, an AI agent to be trustworthy, some of the requirements should be there. One of the requirements is fairness to the data input, like the decision is not biased to one part of the data more than the other. So I think it's more than a balance between the data that we give to the user, to the AI agent. You need to have explainability, interpretability, and accountability. So it needs to be able to explain itself, the AI algorithm, and it needs to have reliability. So explainability, we are already tackling this through the approach that I spoke about before. Reliability and technical robustness. Reliability means it does what you want it to do. So if it will give you the same output for the same input each time. And that's where I think if we incorporate, if the robot asks the user multiple questions, expanded questions to get semantics about what he wants more. So I think we can increase the robustness of the decision of the AI by asking more questions to the user. Okay, another requirement is human agency and oversight. It means human in the loop. it's one of the requirements for the AI to be more trusted. And this is what I am trying to do here. I spoke about the explainable video vision transformer, which I said it's only a benchmark, but we want to reach the causal graph attention network. Then you will have a speech-to-text model. So the pink one is what I am working on it here. A speech-to-text model, which is already, they are open source. So here it's not the contribution. The contribution should be more into the semantics that you can get more from the user in order to make the final decision of what the user wants more robust. So speech-to-text, then you have the intent recognition from the text, then you give it to the Tiago robot, let's say, to navigate. So I'm focusing now on this in those 2 weeks, I mean, in the following 2 days also, and but the final aim is to incorporate more semantics from the user. And that's it. And I thank you for your attention, and I'm sorry for the time delay and questions.
Thank you very much. I don't think anyone is out here. So, now that why do you use this video? Because there is also this video. Why
because the GAN, in order to make the GAN more robust, usually, you need to show him the faults. In order to make the loss less for the discriminator, and in order to let it learn, it works by showing him what is wrong in order to classify. If he is able to classify the simple way, I don't think can it incorporate the context?
So you use the GAN in order to...
Yes, but it's not only the GAN. I showed that it is not only the GAN that can incorporate. Yes, but for example, we have a Bosch for the integration with Indarco. Bosch is implementing on the robot the normal velocity, constant velocity model. It works, but it will not work in the cases where you have people crossing the gateway. So here comes our input to know how, if they really want to keep for the integration the constant velocity model, how do you incorporate the context in that constant velocity model? It's not this comes the communication between partners.
And the second question is about the last the one that I mean, so you have images and you have delivering the image
Yes,
or not.
which is implicit.
So, and then you have a bunch of images and the scene is presenting this situation.
Yes.
And then you want to implicitly make a mismatch of which elements of the scene.
Yes, it's so like the fact. Yeah, it's like.
Okay.
Yeah, but I have a doubt that it will give the better performance than the graphic, or better explainability than than the graph attention method, because here it's like you are giving all the features and the image. It is difficult to let it tell it, like for example, here for example, there is a monitor here and there is a desk. So I feel it will be less explainable than the graph attention method, because the graph attention, I think the graph attention method, you are helping it some way in detecting first the salient objects that you want from the scene, but you know them already. So as if you are minimizing this representation of the scene for the graph attention method, because you need the nodes, and in the nodes you need the variables. What are the variables are the classes that you want to detect. But here you are giving all the image with all the features that may contribute to the class and may not contribute to the class. Another project. Thank you.
Sorry, I was about to question. Thank you for your. One question I want to use, you actually use soft match layer after that. To apply this
Oh, wait. This or the other one?
no.
So the dual stage attention, or this or the.
No, another. Do you think the easy LSD after soft match could be effective? And applying LSD after soft match adds something to your work.
Yes, because we are inputting a time series of the observed trajectories. So the LSTM will help into embedding the hidden states of all the observed time series. But the softmax is used in order, because here you are getting the attention weight.
Yeah.
Yes, because an input attention. So you are getting an input as if you are getting a weight, and then you are normalizing those weights, and then you are giving this to an LSTM layer, which those doesn't incorporate the hidden state of all the trajectories and all the observed time series, but the LSTM does. To be honest, I didn't test removing the LSTM and see what is the performance without LSTM, but I took it as I took it as a priori that LSM is the basic architecture that helps in embedding the time series of observed variables, states.
Yeah, but if the soft max is set equal to number of your categories, I think based on my experience, you cannot have anything to your model. Maybe you don't use the but yeah, I don't know. Maybe on a project, but there is people just maybe you can inform soft max also.
Did you have, if I can ask you, did you have also in your work, did you have an LSTM before it or only after the soft max?
Many people from us could be more effective at this. It has a good check. After that, someone said from the categories, maybe just give you a market of probability from which one and even the effective for your neuron for that. My experience. And that's what I show you.
Yes, it is. I think it is. Yeah, it is good to check. Although, as on a not practical level, but on a more high-level understanding that the values will not incorporate the information accumulated from the previous trajectories in the software. And if I do it like this, so in my understanding, if I don't have any LSTM before the softmax, the values of the softmax that are output will not signify, will not embed any information from the hidden state of the trajectory of the person. And that's why there is an LSTM here, but yes, okay, it's good to check it. Because yeah, I cannot infer. It's good to check it. Thank you.
I don't know how you really when you apply, you apply softmax into the potential weights, and then you multiply the potential mass, you multiply the weights to the rate and you work to weight them, and then you I think if you read the output of the softmax directly into the SDM, maybe.
It may be wrong.
Yeah, I think this is exactly wrong. It just you multiply this completely output of the softmax to the
It is multiplied.
Okay. So this is
Yeah. It is the high level layers. Yeah, but he is suggesting something else. He's suggesting to test without even an LSTM, which I cannot. What he said. After.
For LSTM, if LSTM some unfortunately.
I got it. Thank you.
Right.
Thank you.
Very much. Thank you. Stop recording.